All right, so we're looking at, again, linear system word problems part C, in which we're talking about being able to find speed, okay? Now, there's two different situations we're looking at. One involves a plane, in which we're talking about maybe the speed of the plane in still air versus the speed of the wind. And then in the second situation, we're talking about a boat here, and that's actually the one I want to focus on for now, since there's a question like this on your test, and it talks about a boat traveling upstream and downstream, and then finding the speed of the boat and then the speed of the current. Okay, so let's read through this problem here. It says a boat traveled 198 miles downstream and back. The trip downstream took 11 hours, and the trip back took 33 hours. Find the speed of the boat in still water and the speed of the current. Okay, so we're talking about finding speed again. Now let's kind of go back and break down what each of the different individual parts here mean. So a boat traveled 198 miles downstream, downstream and back, okay? So it went 198 miles all the way downstream, then turned around and traveled a whole nother 198 miles going upstream, okay? So that's what it's talking about. Now, to understand the context of downstream and upstream, if you have a boat's going to travel a certain amount of miles per hour, okay? In still water, it travels a certain amount of miles per hour. But when you go downstream and there's a current, when you're going downstream, the current actually helps push you along. In other words, you're going faster, okay? So when you go downstream, the current helps you and you move faster. When you go upstream, you have to fight the current and you go slower, okay? Because the current is pushing against you, so it takes more time to go upstream, okay? And that actually matches what they're talking about here, where it says the trip downstream took 11 hours, but the trip upstream going back took 33 hours. Now, what we want to find is the speed of the boat. If there were no current, what would it be in still water? And then what is the speed of the current that's, either helping us going downstream or impeding us going upstream? Okay. Now, the way we can look at this is if I since these are the two things we're looking for, the speed of the boat in still water and the speed of the current, if I let x be the speed of the boat in still water, and I let y be the speed of the current, okay, then we can relate this in terms of an equation, okay? X, the speed of the boat is going to be consistent, okay? In terms of if we're in still water, the speed of the boat is going to be consistent in terms of going upstream and downstream. That's going to remain constant here. The thing that changes that makes us move slower or possibly move faster is because the current is either pushing us along or it's actually pushing back against us, and that's why we're moving slower. Okay, so let's say that we have X here let's write the two situations we have. So we have downstream and then we have upstream. Okay, that's really the two trips that we have here, the trip downstream and the trip upstream. Downstream, the boat is going X number of miles per hour. That's what it's going in still water. But when we move downstream, the current adds to our total speed. We're moving faster. So the current is actually going to add to our speed, so we move faster. Then when we turn around and go upstream, whatever the boat's going in terms of still water, the current is actually now going to fight against us, and it's going to take away from our speed. We're moving slower. Now, that's the start of our two equations. And some of you guys might say, well, do we set this equal to 198? Well, the answer to that would be no, because 198 is the distance, right? It's the distance we traveled down, and then it's the distance we traveled back. This is talking about speed. So to help us understand what we need to set these equal to, go back to what you guys maybe have learned in elementary or middle school. Distance equals rate times time, where rate is the speed, okay? Now, they give us a distance, and they also give us time. So if you notice, if I rewrite this, I could rewrite this by dividing t to both sides, and we have distance over time equals rate. Okay, so if I take the distance of our trip and divide it by the number of hours it took to make that trip, that would tell us the speed that the boat was traveling. Okay, in other words, the speed of the boat in still water plus however fast the current was pushing us along, or the speed of the boat in still water minus being pushed back by the current. Okay, so if I take 198 in the first trip and I divide that by going downstream in 11 hours, that would give me the speed of the boat and how fast it was traveling. Okay, so if I take 198 in our calculator, 198 divided by 11, you would get 18. Okay, so 198 divided by 11 says that we were traveling 18 miles per hour between the speed of the boat in still water plus being pushed by the current. Then going upstream, if we take 198, because it also went 198 going back, divided by 33, that time going back, we take 198 divided by 33, we would get 6. Okay? Whoops, there we go. So we're going 6 miles per hour. Okay? So because we're being pushed against the current, we're moving slower. So we're going 6 miles per hour. Now I have my two equations with my two unknowns, and I can solve this. Well, looking at this looks like we could solve this really easily with elimination. We already have opposite coefficients. I could add this together, and x and an x would make 2x. The y's would cancel out, and we'd have 18 plus 6, which would give us 24. Divide out by the 2, and we would get x is equal to 12. So x being the speed of the boat in still water, well, the speed of the boat in still water would be 12 miles per hour. Then we could plug that back in, and I'm actually going to write this below here. We could take this and plug it back into either one of these. I'm going to plug it into the top, and we'd have 12 plus y equals 18. Subtract 12 from both sides, and we would get y equals 6. Okay, so what is the speed of the current? 6 miles per hour. Okay, so the speed of the boat in still water, let's just write this below. The speed of the boat in still water is 12 miles per hour. So if we didn't have any current, we'd be going 12 miles per hour. But the current here, the speed of the current, is 6 miles per hour. Okay, which makes sense according to our two equations that we wrote here. Okay, so 12, the speed of the boat, plus the 6 for being pushed with the current, helped us so that we were going 18 miles per hour. That's why the trip was shorter. But then we had 12 minus the current now fighting against us, so now we were only going 6 miles per hour. Okay, so that's how we'd work through these types of questions here.